So in this video we'll be talking about alkynes, and in the previous video we spoke about alkenes, which were doubly bonded carbon chains, and alkynes are just triply bonded carbon chains. And so over the next couple minutes I'll be explaining several reactions that alkynes can undergo and why they're useful in organic chemistry. So the first type of reaction that's important is the reaction of an alkyne with Br2, and it actually reacts very similar to how Br2 reacted in the presence of an alkene. Both bromines are going to add and take away one of the bonds present in the alkyne. And so you can see in this product over here that both the bromines added on either end of the alkyne, and they turned that alkyne, that triple bond, into a double bond. And if we were to run that Br2 again, like in this scenario down here, we'll see that it'll actually add another bromine to either end of the double bond, as you have seen in the Alkyne reaction with Br2, and make two bromines coming off either end. And so if you're looking to make a product with two bromines coming off the same carbon, and you're starting off with an alkyne, you would just run Br2 in excess. Another reaction that's important is the reaction of HBr with an alkyne, which reacts very similarly to how Br2 reacts. It'll add a hydrogen to one end of the alkyne, and it'll add a bromine, or whatever halogen we're dealing with, to the other end of the alkyne, and that's shown here in the product. If there's a scenario where there is a more tertiary carbon, as we discussed in the alkene video, the bromine will add to the more tertiary carbon. And if we were to run another HBr with this product that we now have over here, then the bromine will add to the side where the hydrogen added originally. So it'll add to this one. The second bromine will add there. And the second hydrogen will add here. And so on both carbons, you'll have a hydrogen and a bromine. The next reaction which is useful is the reaction of H2O in the presence of H2SO4 with an alkyne. And what that does is that'll create two products. That'll create our enol product, and that'll create our keto product. And these two products were tautomerize between each other, and that's known as a keto-enol tautomerism. And so, as you can see, what it does is it adds an alcohol here to one end of the alkyne, and that alcohol can actually interact with this double bond here to make the keto version. And so over here I've drawn out for you how the keto and the enol will kind of tautomerize between each other. The enol is the product with the alcohol coming off one end, and the keto is the product with the doubly bonded oxygen coming off, the carbonyl group coming off of one end. And so these will tautomerize between each other. Typically the keto is more favorable. The next reaction is a reaction which is Psi-BH in the presence of H2O and H2O2, and this is kind of the alkynes version of a BH3 reaction, as we discussed with alkene. And with an alkene, we can apply BH3, and an alcohol will form in the Markovnikov position of your alkene. And so Psi-BH is typically used for terminal alkynes, as shown by this starting off reagent. And what it does here is it'll actually make the keto-enol tautomerism. What I've drawn here is the predominant product, which is the keto version. And if you look at this is actually an aldehyde, and that's why I wrote here an aldehyde product. And so if you are looking to make an aldehyde out of a terminal alkyne, Psi-BH would be a very appropriate reagent. The next two reactions I wrote here are ways to actually convert alkynes into either an alkane or an alkene. And so you can see in the first example I have here, I applied H2 in the presence of PD, and PD is just a metal catalyst, and that'll turn our alkyne into an alkane, as shown by this final product. In the second example I have here is H2 in the presence of a Lindlar catalyst. And the difference between H2 in the presence of a PD catalyst and a Lindlar catalyst, as shown by this example down here, is that the Lindlar catalyst will turn our alkyne into an alkene. It'll also turn it into an alkene, and both hydrogens will end up in the cis position. And so if you're looking to make an alkyne turn into an alkene in the cis position, H2 in the presence of a Lindlar catalyst would be a good option. Now, what if you want to turn it into an alkene in the trans position, so your hydrogens add in the trans position? Well, then what you can do is you can apply NaNH3 to your alkyne, and that'll turn it into an alkene with both hydrogens in the trans position. And so to turn your alkyne into an alkene in the cis position, you do H2 in the presence of Lindlar. To turn your alkyne into an alkene in the trans position, you do NaNH3 to your alkyne, and that'll turn it into an alkene. And so the final reaction I'm going to talk about here is the reaction of NaNH2 in the presence of an alkene. And why this is useful is because this is a useful way to turn an alkene into an alkyne. By applying NaNH2, a reaction will undergo that's past what we're going to discuss in this video, but what it will do is it will turn our alkene into an alkyne, and we can use that alkyne for further synthesis and apply all the different techniques that we've learned in this video. And so I hope that through these different reactions you can appreciate the different reactivity of an alkyne and how it can be useful in organic chemistry.